So as you can see on the screen, the solution as well, that we are taking the minimum people 3 cross the VIP people and normal people, and multiplying it with time per person, that is X.
Thanks a lot, Janmans, for the solution idea. Let's go
Thank
to
you, Praveen.
let's go to the second problem, which we thought in terms of difficulty level. The balanced subarray problem. Who wants
I
to?
think it's your book reading problem, Praveen.
Sure. So let's do like, I think both are similar difficulties. So let's
Yeah.
go to book reading problem. So in this problem, you have, so basically like you are facing exams and you have come to a library to study. So you make like multiple operations. Each operation could be of two kind. Type 1 kind is basically you read the next X books, and type 2 kind is you undo basically your last operation. So you could do like, for example, if you do type 1 operation for 3 books, then you read the books 1, 2, 3. Then let's say you do another type 1 operation with 2 books, then you will read book 4 and 5, and you can basically undo your last operation, which means that you go back to read start from book. Let's say you do type 2 operation, undo the last operation. So in the last operation you had read the books 4 and 5. So now you will go back and you will, next time you will start reading from 4 only. So what we wanted to do is like, at the end of this library session, we want to find out what's the total number of books that you have read at least once, basically. So essentially, this problem is like really kind of intuitive. So basically, let's say if you did not had the undo operation, then the total number of books you are going to read is just the sum of books in each type 1 operation, which is like really easy. So now if you do undo, then you will need to go back and start reading. So how can you implement this undo operation? This can be implemented using stack. So what you do whenever an operation of type 1 X come, you add X to the stack. Whenever an operation of type 2 comes, then you pop out from the stack. And essentially, in order to track what's the total number of books you have read, you would want to essentially, so total number of books at any point of time would be whatever you have in the stack, essentially. So what's the maximum number of books that you had inserted in the stack? That would be your answer, essentially. So let's see the code for this and you will be more clear with the idea. So you read the input, and if the operation type is 1, then you read X, and current book index would be plus equal to X. And we will need to find this max books index, which is the maximum amount present in the stack. So max book index would be maximum of current book index and max book index. And I will insert X into the stack. So this is how we will handle type 1 operation. In type 2 operation, we basically like remove the topmost element from the stack and decrease the current number of books by the amount that was present at the top. And finally, you print the maximum book index, which was what's the maximum number of books that you have read till now. So essentially, this was really clean and intuitive use case of how do you use stack. Hope you have enjoyed this problem. Time complexity for this, as you know, would be order of number of operations, because insertion into the stack is order 1 operation, and popping the topmost element from the stack is also an order 1 operation. So your overall time complexity would just be order of n. I let's so that was it for book reading problem. So by the way, if you have questions, feel free to ask them. We will definitely tackle them. Let's go to the next problem now. The problem is balanced subarray. And who wants to take it? Janmant, you or Chaitanya?
Yeah, I'll take it up, Praveen.
Sure, sure. Let's go.
So if you could, yeah. So in this problem, as you can see, the key point here was to notice that it's an array of positive integers. So let's read out the problem statement once. You are given an array A consisting of n positive integers. A subarray L comma R is said to be balanced if the sum of elements in that subarray from index L to index R, both inclusive, is equal to the length of the subarray. So if you read this, so basically, the as we said, the array contains only positive integers, right? So all numbers in the array are greater than equal to 1. Now for a subarray to have its sum equal to the length, the main thing to notice here was that all members of the subarray should be 1. Even if one of the members is 2, and since array cannot have number less than 1, then the sum will become greater than its length, right? So this was a thing to notice, I would say. Now you're given q queries. In each query, you have an integer x or an index x. You need to find the number of balanced subarray between index 1 and index x. That is from array 1, a1 to a1, a2, a3 to till a of x. So the subtask 1 was pretty easy, that you find all subarrays basically. In each query, uh, you maintain a map of how many ones are coming, and you can solve it accordingly. For subtask 2, Praveen, if you could go to the solution. So in subtask 2, what we can do is we know that the all the members of the subarray has to be 1, right? So we can count the number of ones till each index, and how many subarrays can that one contribute to. So let's say take an example, say 11311. I think you can comment it out and write it here only, Praveen, on the text editor itself, maybe. Yeah. So let's say we are taking an example 11311, and let's say that I want to know the subarrays from index 1 to 3. So we'll start from the first index and start counting. We see the first one. Now we see from index 1 till 1, this one contributes to only one subarray. Now we encounter another one. This one encounters, like, contributes to two subarrays. One is index 1 comma 2, and one is index it's only 2. Now we come to index 3, which is not 1 exactly, so we ignore it. So its answer is basically till the before index, like we how many subarrays we had till the previous index will remain the same. So that is basically 1 plus 2. So till index 3 we have 3 subarrays present. Similarly, if we continue, we go to index 4, we encounter a 1, we see how many subarrays can this one be part of from index 1. So it can be part of only one subarray itself, right? Because before it there's a non 1 integer, that is 3. And again, if we go to last index, we'll count how many subarrays can it contribute to, and it can contribute to two subarrays. One is 4 comma 5 and one is only 5. So this is how the logic goes, and we can easily do it with prefix sum. So at each index we can maintain the count of ones and then do prefix sum, and that is what the solution also states, if you see, look closely. So here we took the input and like we counted the ones at every index. So if AI is 1, we increase the count and we put the count at that index on answers. And then we do the prefix sum for answers, because that one will be part of that many subarrays. I hope the solution is clear with everyone.
Yeah, also like the time complexity, as you can see, would be order of n, because you are just like have a single
Right.
loop. And so thanks a lot, Janmans, for such a great explanation. Let's go to the next problem. Which one should we do? Wood bell policing first or perfect pair first? Let's do wood policing problem. Janmans, do you want to go or should I explain?
If you could, yeah, go ahead for
Yes,
this one.
sure. So let me try to. So essentially, we have a unpolished log of wood of size n, and what we want is we essentially want to polish this log of wood. So essentially, what you we are given basically polishing cost for a wood of size 1, size 2, size 3, up to size n, and essentially want to get this log polished in minimum cost. So what we can do is we can split this log into smaller parts and get those smaller parts polished separately. And essentially, in the end, we basically we can combine all these parts, and so we are given cost for whenever we want to split a log into two parts, we will need to pay cost X, and whenever we want to join two or more logs into a single log, we will need to pay cost Y. And essentially what we want to do, so you take this piece of log, you split it in whatever way you want, and for individual sizes of wood, you pay their corresponding costs, and finally you merge it and find what's the minimum uh, cost of polishing a log of wood of n. So essentially, this was basically a dynamic programming problem, and the main idea behind this problem is essentially, let's say let's say we want to find what's the minimum. Let me just a second. Yeah. So let's say, so we are given cost for processing cost, let's call it P cost, for wood of size 1, if you want to polish wood length of wood of length 1, length 2, length 3, length 4 till length n. So this one is, let's call it processing cost P1, P2, Pn. In the end, what we want is we want essentially, so let's say if I have this blog of size, let's say small n, and what I could do is I could either split it into two parts. I want to find minimum cost for this. What I can do is either I can process this entire log by itself. So the cost for that would be P of n itself, P of n. If I process this log directly, the other strategy could be instead of processing it directly, I split it into two parts. So let's say one part has size X, then the other part will have size n minus X. And then essentially I paid, so what would be the cost in this case? Would be the minimum cost for processing size X. This I have to pay plus minimum cost for size n minus X. And then I will also have to pay for splitting this. So whatever is the cost for splitting, split cost. And so minimum cost for n would be essentially minimum of these two quantities, quantity number 1 and quantity number 2. And this x we can essentially could go from 1 to n minus 1. Essentially, the first log could be of, so when we are splitting into two part, one part could, length of one part, that is x, could go from 1 to n minus 1. And so that the other part will also be of the positive length. So essentially, we just need to implement this dynamic programming idea. And so you can implement this dynamic programming idea as follows. So you create an array called min processing cost. this is your dynamic programming state, DP. You go over size from 1 to n, and the minimum processing cost for that size, let's initialize with the processing cost for that particular size. Now I go into splitting component. So x will go from 1 to size, and minimum processing cost would be minimum processing cost of x plus size minus x plus splitting cost. So I do that. And finally, what I want is minimum processing cost of n. So essentially, in the end, if I so if so this min processing cost, I could essentially, first thing is if I can basically polish the entire log itself. So the cost for that would be P of n itself. So I won't be paying more than P of n. And if I'm splitting and paying, then so basically take the minimum cost of n, and essentially I will finally also need to join those individual parts. So finally you also pay the joining cost as well. So final answer would be processing cost of the last processing cost of n minus 1 plus minimum processing cost of n plus joining cost you will also have to pay. Take the minimum of these two, and that would be your answer. Time complexity of this would be the first for loop goes to order of n. The inner loop also goes to O of n. So overall time complexity becomes O of n cross n. And space complexity would be, as you can see, we are just storing processing cost for size n. So space complexity would just be order of n. Also note that your intermediate calculations may go outside of bounds of integer. So make sure that you have either you deal in like long or int 64. Otherwise, like your answer may overflow. Let me see if there are any questions related to that. Yeah, there's no question for that. So I think, Janmans, do you want me to, what do you think is there any other points you would like to point out here? Sure, then let's go to the next problem, which was perfect pair. Chaitanya, would you want to take it?
Sorry, yeah, you can go ahead. I'll take V-shape sequences.
Sure, sure. So essentially this problem is we are given essentially an array of size n, and a pair of indices I comma j is called perfect pair if the product of ai and aj is a perfect square. And essentially, what is a perfect square? If a number can be written as x into x, where x is basically square root of n, essentially. So, for example, like 4 is a perfect square, 9 is a perfect square, 16 is a perfect square, 25 is a perfect square. So what we want is we want like number of perfect pairs in A. So ON square solution we could do like, so it'd be fairly easy. What we do is we iterate over indices I and j. We go over index I, then we go over index j, we calculate AI into AJ, and we check whether it's a perfect square. Checking whether a number is a perfect square is like essentially we take square root of that and we cast it to integer and we multiply it by itself and see whether it is equal to the original number or not. That way we can check whether a number is a perfect square or not. And this would be order of n square solution. Now we want a solution better than order of n square. And let's see how we can do that. Essentially, first thing is, let's say you have, so let's say you have a number whatever. Let's say you have number x, and its prime representation has, let's say, some prime powers. P1 power Q1, P2 power Q2, and so on and so forth. For example, x could be, let's say, 2 power 5, 3 power 2, and let's say 5 power 1. First thing you can see that all essentially, and you have this number x and you have your number, let's say another number y. For a number, let's say your product of this x and y is z, and we want to check whether z is a perfect square or not. So let's say z has its representation as some prime power q1, some another prime power q2, let's say 2 power 4, 3 power 5, and so on. First thing you should see that for each prime number, the power should be even in order for it to be a perfect square. If the power is not even, it won't be a perfect square. So for example, in this case, 3 power is 5. So this number is not going to be a perfect square because there's no way for you to get 3 power 5. So essentially, the Z should have these all the prime powers in its prime factorization. They should be even in order for it to be a perfect square. So this is like the very first observation you need to make. Another observation you need to make is essentially, let's say x has 2 power 5, 3 power 2, 5 power 1. Essentially, if you multiply by y, in the end, for let's say x has some p1 power q1, p2 power q2. Y also has similar representation. If you multiply x by y, you will have, let's say, prime power q1 plus, let's say this has p1 power r1, p2 power r2. So q1 plus r1, p2, q2 plus r2. So you can see that for what we need is for x into y, we just need the parity of this, which is we just need to know whether this number q1 r1 is even or not, even or odd. So we just need q1 plus r1 modulo 2. So if we just know that, we can basically figure out the parity of the product. So what we can do is, if we know, let's say x1, x equal to p1, q1 mod 2 and q2 mod 2, and similarly r1 mod 2, r2 mod 2, then essentially we can find whether the corresponding product would be a perfect square or not. So what we do is we take the number x, and essentially if 2 power, let's say if it is 2 power 5, 3 power 6, 5 power, let's say 7, what we do is essentially we convert it into an equivalent number where 2 power 5 will become 2 power 5 mod 2, which is 1, only 2. 3 power 6 will become 3 power 6 mod 2 is 3 power 0, which will become 1, 2 into 1. 5 power 7 will become correspondingly 5. So if I will only take so essentially the product, it would be a product of primes whose power is basically odd. All the even powers I am not taking. So only the primes who occur odd number of times in X, I am taking those primes. So similarly, if Y also has some representation, and it also has basically, let's say 2 power, let's say 7, and 5 power, let's say 9. So you can see that I will be taking, and let's say 7 power 4. So in this case, I'm going to take only the numbers whose power is odd. So 2 into 5. Now you can see that both these numbers have 2 into 5 product. If I multiply them, this will become basically 2 power 2 into 5 power 2, which is prime power. So essentially, for each number x, first you find its smallest representation. in the sense that you remove all the even powers and you calculate the remaining number. Similarly, for y, you do that. And finally, all the numbers that have same representation then can be multiplied together to form a perfect pair. So if you see in my code, I have this function called square free parts. So square free parts is essentially, for example, for this number x, square free parts would be 2 into 5, 10. So just remove all the even powers and only the odd powers. Take the product of them, that would be the square free powers. And essentially what I do is I just need to count. So I go over each of the element and I see what's the, I take the square free parts for that and I count how many numbers with the same square free part I have encountered till now. And that many, with those many numbers, I can form a perfect square pair. So I will increment my answer by map of square root SQF. And then I will increment this m of map of SQF. And finally, this would be my answer. One thing is like, in order to find prime powers quickly, what you can do is you can calculate prime using prime sieve. And the idea behind like prime sieve is like pretty simple. Like, for example, if you, let's say you write down all your primes, like let's say you write all the numbers 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Let's say we take these many numbers. So you start with the first number, which is 2. And we take all the multiples of 2 and we mark them that they are not a prime, because you can see that first multiple of 2 is 4. So we can see that 4 is not a prime because 4 is divisible by 2. So we go over the table of 2 basically. 2 into 2 is 4. We mark it not a prime. 2 into 3 is 6, not a prime. 8 is not a prime. 10 is not a prime. So all the even number in the first step, we say that they are not a prime. And we say that 2 is a prime. Now we go to the next number. We say that, okay, you are a prime. And then for all its multiple, we say that they are not a prime. So we go in the table of 3. So we say 6 is not a prime, 9 is not a prime, and 3, 4, 12, and 3, 5, 15 is not a prime. Now we go to the next number 5 and perform the same operation. So this is called sieve algorithm, Eratosthenes, and this is my implementation for it. Time complexity for this prime sieve is order of n log n, and that's why like it's faster. And for finding like square free parts, essentially for each prime number, you go to all its multiples, and essentially you find the prime power. And if the prime power is odd, then you take that corresponding prime as one of the square free parts. And finally, you process the algorithm. Let me know if there's any questions. I will check. I think there's no question. So next problem we can go to is nice ancestors. Anyone wants to take this problem?
Yeah, I could take this.
Sure, Vikas, let's go ahead.
I'll just open the problem. Sure. So I hope this is visible. This is visible, right? I'll assume it. Right. So the question is that you're given a rooted tree, right, of n vertices labeled 1 to n, and yeah, it's rooted at 1. And for each vertex, you have to find the kth closest ancestor, which is nice, right? And how do we define a nice vertex? It is called nice if it has exactly one child, right? So yeah, we are given the tree. So now what we can think of immediately is that an n square solution is pretty easy, right? 1 2 3, and in general if you have more nodes here, then what you can do is you can do a DFS and keep a track of the parent of each node, right? So suppose for 2 the parent is 1, for this is suppose 5 the parent is 2, and so on, right? And what you can do is at each node keep iterating through the parents until you find the kth node which is nice, right? So what I mean is, suppose you have uh, an array pair n, this is the size, where pair I indicates the parent of the ith vertex. Then what you can do is you can have something like, and suppose you define a 0 node to be parent of 1, you can do something like while x is not 0, x is not 0, you iterate over the parents, right? Like you check if parent of x is nice. If it is nice, then decrement the k that is needed, right? So suppose this is the k local variable, so you decrement k. If k becomes 0, then this is the kth vertex we need to find. So we are done. Otherwise, if you reach 0 before k becomes 0, then the answer is obviously -1, right? So this is the brute force solution n square, which should get about 20%. Then one optimization you can think of is that you can kind of keep a track of the last vertex in the DFS, which had ancestor as, excuse me, ancestor as, not ancestor, where the last vertex is nice, right? So the idea goes like you can have a vector v that you pass in the DFS, right? You can either keep it global or you can pass it in the DFS by reference. So suppose it is global for easiness. So you can add elements, or say suppose you are at a vertex I, you add I to v when you are visiting I if I is nice, right? So you push it to V, and then you continue DFS, iterate over I's children and whatever. And once again, at the end of the DFS, if I is nice, then you pop from this vector. So what vector V will store in a DFS is all the vertices in the path from the root 1 to the ith vertex, suppose, or say jth vertex, because we've used I here. So it will store all the vertices in the path from 1 to j which are nice. So it's basically all the ancestors of j except for j, of course, that are nice, right? So what you can do is, before we add I to the vector v, right, over here, say suppose you want to solve the second subtask, which is k equal to 1, then we only need to check the top of this vector. Whatever, if the vector is not, if the vector is empty, then the answer is -1 and we are done. If the vector is not empty, we can just take the last element, right? So that has to be the closest ancestor of j, which is nice, and we can use that, right? That will be the answer for the jth node, right? And yeah, after doing this check, you add j to the vector if it is nice. Then you do a DFS, and then you pop from the vector if j is nice. So this way, that property of the vector, that it stores the all the nice ancestors of j when you are visiting a vertex j, that property is maintained, right? So for general k, the solution is just one step extra from this. So with k equal to 1, we take the last vertex, but we can use the same argument, right? So suppose this is index 1 2 3 4, and suppose this is some index m, right? So the index m will give you the last vertex, which is nice, and index m minus 1 will give you the vertex, the second closest ancestor, which is nice. This is at index m minus 1. Similarly, m minus 2 will give you the third closest ancestor, which is nice, right? And this will keep on going until you have the I, the first vertex, right? So more generally, you can say that suppose V is the vector, then V dot size minus K will give you the kth closest ancestor if V dot size is greater than or equal to K, right? And if it is less than K, then you know that in the path from 1 to J, there are no K ancestors which are nice, so the answer must be minus 1. So that's about it. So in the previous solution, you just make one modification, that you check the size, right? If the size is less than K, then it is minus 1. If it's greater than or equal to K, you simply check the element at this index in V. So V of V dot size minus K will give you the kth closest ancestor, which is nice. And yeah, that's what you need. So you'll be done. Anything else I have to discuss? Any questions, anyone? Right. So yeah, I'll stop now.
Thanks a lot, Vikas, for such a great presentation. Let me also share its code. So essentially, this again, as in if you just want to take one thing away from it, this problem is if whenever you are doing DFS, let's say you maintain a stack, essentially whenever you enter a vertex, you add it to the stack. Whenever you exit out of DFS, then you essentially pop from the stack. So you can see that at any point of time, the stack would be consisting of all your ancestors only. That's the most important observation. So if you understand that observation, the remaining parts are easy to formulate. So here you can see we are taking the input, we are creating a graph called G, and we are maintaining this adjacency list. So for we are reading parent for ith vertex. So essentially I and parent of I would have an edge. So we push Gi parent of I and parent of I to I. And finally we do this DFS and we maintain a stack. And in the stack, we are going to insert at line 184, you can see. So if the number of children for a node is 1, then it is a nice node, and we are going to push into the stack. And in the end, we will pop from the stack. And essentially, for calculating answer, we check whether the stack size is at least k, and we take the starting from the last kth element, and that would be our answer. This is overall solution to this problem. Thanks a lot, Vikas, again. Let's go to the next problem, V-set sequences. And Chaitanya, would you like to take this problem?
Yeah, sure. Let me share my screen.
Sure, sir.
Can you see?
Yeah.
Yeah, it's visible now.
Okay, thank you. Yeah, so this is the problem. You are given an array of points on a 2D plane. We have to count the number of V-shapes. So the definition of V-shape is given below. You have to find triples ijk such that the x-coordinate of I is less than x-coordinate of j is less than x-coordinate of the kth point. And the y-coordinate of I is greater than the y-coordinate of j and y coordinate of k is greater than y coordinate of j. So when you look at it from a graph like perspective, it's like drawing a V. So let me share my screen here. Can you see the drawing app that I've opened here?
Yeah, it's
Okay.
visible chat.
Okay. Yeah. So yeah. So if you look, if this is like I, J, K, then we know that x coordinate of I, J, K, then increasing order, and y coordinate of I is greater than J, y coordinate of K is greater than J. So it's like a V. It looks like a V. That's why we call it a V shape. So the brute force for this is like quite simple. Um, there is a very simple n cube brute force. You loop through ijk and you just check if this condition is true. That's like very simple. And if that solution is optimized, then maybe 20 points, you could have gotten 20 points. So it does say like n is less than or equal to 2000 here, and n cube is like 8 into 10 power 9, which is very, very close to the limit. So it is not an intended solution, but sometimes like if it was very optimized and very simple, then maybe it could pass. Like that is also fine. So now let us look at the n square solution. So the way we count here should be important. So let us, in a V shape, let us iterate over the bottom point. So what I'm trying to say is like for every bottom of the V shape, how many like V shapes are possible? So let us take an example here. Let me change that for you. So let me take this point. So for this point, how many V shapes are possible where this is the bottom point? So I think one is like this is one, and this also is one. So there are many to count here, but I'm just giving example. So this is one, this is one, this is one. So all these have to be counted. Um, and let us look at another example. I guess if you look at this, there's only one, right? Only this. There are no other V shapes. So the way to count this is we have to sort the array first. So let us like sort, like if A is the set of points, let us sort the array first based on the x coordinate. And then if two x coordinates are equal, then we can sort them by y coordinate. So if we just look at this point, yeah. So that will be some index j in our, this point will be some index j in our array. So like a of j is equal to that point. Now, what we want to do here is we want to find all the points on this left quadrant and all the points that are greater than this height. So we want to count this and this. Then in the right quadrant, we want to count these points. So if this is some LC and this is some RC, left count, right count, the number of V shapes possible where this is the bottom point of the V is LC into RC. I hope that is clear. This is an important observation to make. So for every point in this left quadrant, it can be matched with every point in the right quadrant to get a V shape. So this is a V shape. 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 Similarly, like this, like this, like this, and yeah. So these are all the V shapes where this is the bottom point. So we want to calculate that. So to calculate that, again, it's quite simple. So we just loop through the array again. We loop through the set of points from here. So we know that for all I less than or equal to j, the x coordinate will be less because we have sorted the array. Similarly, we can just count for all k like less than or equal to j, which of these have bigger points. So we literally, for every point j, we literally just iterate through all these points, find out which of them have higher, greater y, and put it in LC. Similarly, we iterate through all these points, we find out which of these are higher. We find out this are greater y coordinate, and we increment RC. So that way, for every j, we get LC and RC in O of n time. So for every j, we get LC count, LC RC in O of n. But again, we are iterating over j, right? So j, there are n possible combinations for j. So overall time complexity will be like O of n square. So I hope this is clear. Yeah, so when you do it for all j, you realize that we are counting all V-shaped sequences. So since all V-shaped sequences have a bottom point, and we are iterating through all bottom points, we are counting all V-shapes. So that's also an important thing to notice. So the optimal solution for this is also like an extension of this idea only. We are just counting them smartly, like we are not iterating through all these points. Again, we are fixing a j. We iterate through a j and we fix the bottom point. Now we have to find all possible LCRC count, the way I said before. But now we have to do it a little bit more smartly. So one data structure that we use, we can use many, but my optimal solution uses an ordered set. Like it is not in the standard library. We have to import it from a different library, but it's an ordered set. So basically, this data structure is like very useful in the sense that whatever elements you put in this set, like let's say S is the set ordered set that we have, ordered set int S. Then there is a method for this data structure called S dot order of key. Let me just verify again. Yeah, it is called order of key. S dot order of key returns the number of elements in S strictly less than k. So k is an element here. So k is an element in S, or it can be some data type of S. So it is some integer. Now S dot order of key will give me all the elements in the set that is less than k. And this is very useful for us. We'll see why. So let us just assume that this data structure exists. And it does exist, like you can check online ordered set or something. And you can also implement the equivalent of an ordered set using a segment tree or a binary index tree or a Venn tree, something like that. But for now, we'll assume that this data structure exists and we get this method in O of log n time. Forgot to say that. So S dot order of key of k will give the correct like results in O of log n time, where n is the size of S. Okay. So what we do now here is, suppose we had all these elements in the left side in an ordered set, and suppose we had all these elements on the right side in another ordered set. So like if this is left ordered set and this is right ordered set, then can we find the answer is a question. So yes, so if we have such a data structure, then we could just like query, right? Like if we so these heights are all in left. So what we can do is just we query this data structure left dot order of key, and we give the input as this y, like j dot a of j dot y, a of j dot y. So this will give me the count of these points, the number of points less than this y. So then to get these LC is quite simple, right? It's just left dot size minus left dot order of key of a of j dot y coordinate, right? So this will give me all the points. This will give me left count basically, this and this. Similarly, we can just do the same thing on the right side. So on the right side also, right dot size minus right dot order of key of a of j dot y will give me the count of this. So basically we have got the count of LC and RC in log n time, in just O of log n time. And so like we just have to do like the answer plus is equal to LCRC for every j. Answer plus equal to LC into RC for every j now. So the total time complexity here will be O of n into log n. So now there is one question left, like how do we get this left ordered set and right ordered set? The good thing about sorting our array and then going through left to right is that we can build this left and right array while iterating. So I'll show the code. When I show the code, it will become more clear. But here, as we move from left to right, we add elements to left and we remove elements from right. So before iterating through the array, we'll put all the points in the right array. So this initially will have all the points, all the endpoints before iterating. Now while iterating, we'll remove elements from right. From right, we'll remove these elements and we'll put those elements in left. So let me show the code here. Okay. Here I just take input of the array. Here I have overloaded the vector of pair data structure, so I can just do scene. But actually, like there is some code above that, so yeah, scene array of integers that allows me to just do scene A. But we can just take the normal way of doing input. Here I sort the array based on x and y coordinate. Here I make a map of x to all y coordinates. So like let me show that. So here I make a map from x coordinate to an array of y coordinate comma index. So this will be important for us later on to like insert and remove from the left and right arrays. So and this is just like the set of all x coordinates that have appeared for us. So here ordered set is there. Ordered set definition, if you look, this like here it's showing like library not included, but in general it will be included. So this, if you include these 4 lines of code, then we'll be able to use ordered set and it'll give us these 2 methods for us: find by order and order of key. Here we don't need find by order, we just need order of key. So that's why, since I need this, I'm including these 4 lines of code, like these 2 header files and these 2 lines that make it easy to use ordered set. You can look it up online. Like this should be easy to find. It's called policy-based data structures. Yeah, here I'm defining the left and right. Now here, as I told before, we are inserting all the y coordinates of the points and the index. Since like it's technically it's still a set, we cannot add duplicate elements, but there can happen that our y coordinates repeat. So to make the elements unique, I'm just appending the index as well. So I'm making a pair of height and index, and we know that every index is unique. So every element in this right array will also be unique. So we don't have to worry about duplicates. And here I'm filling the array the way I said. Like from here, the x coordinate I am pushing into the array y coordinate and index. And this is just a list of all x coordinates. So here also x coordinates can be duplicates can be there, or like it may not be sorted and stuff like that. Oh, okay, it will be sorted, but it can be like a duplicate. So to remove duplicates, I just use like this erase. Okay, that's it. Yeah, all of x dot erase unique all and x dot end. So this will just erase all the duplicate elements in the array. So I only want all the x coordinates that are there in input. Now this is the code, like yeah. So for all x coordinates that are there, we iterate through all y coordinates. So why I'm doing this is, so suppose points are like this. So the way I'm iterating is like this. So this is the first time, so this is the second, this is the third, this is the fourth. Then I iterate like this. And uh, the way we should do it like this is because I will show you here. Yeah, so for every y in that line, in that vertical line, so here we are iterating through all x. Now this array, this MP of x will give us an array of all the vertical lines, right? All these points are above each other. Since they have the same x coordinate, all these points are above each other. So if I write like 1, 3, 7, 8, so MP of 1 is this whole array, is this array of points, right? And MP of 3 is this array, MP of 7 is this array of points. So all these vertical lines, right? So currently these vertical lines, these vertical points are all in the right array. So we have added them in this right ordered set. If you can see here, insert, we have added all the points, but we don't need this vertical like line of points, right? So we remove them. So we iterate through all these points and then we remove them from the right ordered set. So I have,
Yeah, Chetan, I
yeah,
think like we are probably going like too much into details. Uh,
okay, okay.
we,
Yeah, okay, cool. I'll just make it short. Yeah,
yeah,
so similarly,
we will anyway like publish editorial. So for both this policy-based data structure, how do you use binary index tree or fenwick tree and segment tree, so that like people can follow.
yeah, yeah. Yeah, so yeah, basically I'll just make it short then. Basically, we want to find the number of y less than or equal to on the left side. So if we are here, if you are here, then our ordered set will give us these points. So like suppose we are here, our ordered set will give us these points, and our function that we call order of key will give us uh, these 2 points. And over here, our right ordered set will give us these points. And when we call the order of key, we discard these 4 points and we get this point. So basically, we are counting LC and RC for every point here, and then we are multiplying it, as you can see here. Yeah. So number of y greater than our current point from the left side, and the number of points greater than y on the right side. We are just multiplying them and adding them to our answer. And similarly, we are adding this whole line of points to the left array, left ordered set, uh, after we calculate. So yeah, there's basically this is the answer, and there was maybe an issue in the test cases, but we will fix them. Like we will update the test cases and maybe the scoreboard as well. But yeah, so that was the problem. Any doubts? Uh,
I
yeah, I
think
guess
like
not.
thanks a lot, Chaitanya, for such a great explanation. I think we are done with the essentially all the questions. And before like ending to the stream, I would like to like thank everyone, and I would like to I'd like to call on upon Deepa to provide concluding remarks. Thank you, everyone. Have a nice day ahead.
Thank you.